Hi, everyone. Welcome to our podcast, We Measure the World, a podcast produced by scientists for scientists.
Oh, man, ants, fire ants, just crazy creatures that can just get in to any kind of crevice or a little small space, and they get in there and they just wreak havoc. They will eat anything. It's impressive.
Yeah, it's amazing. They love cable jackets. Like, what is it about plastic that they want to eat?
They eat it for dinner. It's just it is nuts. You're like that cannot be good for you, and they're just chewing on it like rodents. It's so crazy.
That's a small taste of what we have in store for you today. We Measure the World explores interesting environmental research trends, solutions to research issues, and tools to better understand the entire soil-plant-atmosphere continuum. Stay current on applied environmental research, measurement methods, and more. Thanks for joining us. Today's guests are Campbell Scientific Environmental Product Manager Chod Stevens and Meter Director of Environmental Development Doug Cobos. Thank you both for being here today.
My pleasure.
Doug, can you tell us a bit about your background and role with Meter in terms of instrument development?
Sure, I can tell you a little bit about my background first. I am a soil scientist by training, but all of my advanced degrees crossed over into the boundary layer, into the atmosphere. So I've got, some educational background in micromet, which I think is applicable to this particular podcast and this project. And I've been with Meter for 18 years now, doing instrumentation development for that entire time and research and development work. So this will be super fun.
And Chod, what about you? What's your role with Campbell Scientific and what's your background in the realm of environmental science?
Thanks, Holly. My background is also similar to Doug's. I did soil research, primarily soil physics at Utah State University. I had earlier degrees in agronomic research, crop science. So I have a lot of ag background, but found a love of soil in my graduate work. And was able to come to Campbell Scientific, working with soils primarily initially, and then eventually becoming a product manager over our environmental sensors. And that includes our meteorological, soil, and our water sensors.
Today, we're going to be talking about sort of the story behind the Meter ATMOS 41 all-in-one weather station. And it's also sold by Campbell Scientific as the ClimaVUE 50. And this is really just where it's been repackaged to run optimally with the Campbell system. I know that one of the main drivers behind the design of this weather station was the involvement with TOMO. So can you talk a little bit about what that program is and kind of how that all got started?
Sure, I can field that one. So, TOMO is a really interesting story and actually a super fun organization and a super fun mission. So we've been friends with John Selker at Oregon State University for a lot of years. And John is a kind of the consummate gadget guy, right? So he kind of gravitates toward us because we're also instrumentationists. And so we've, talked with him about instrumentation for decades, basically. So, one year, John comes up at probably AGU meeting. He's like, hey, I got this new initiative starting. It's called, TOMO, the Trans-African Hydrometeorological Observatory. And we're going to put 20,000 weather stations, across all of sub-Saharan Africa. And we heard that you guys are working on this all-in-one weather station. So we want it to be the instrument that we put all over Africa. And we're like, okay, John, whatever. And, of course, in typical John Selker fashion, if you know John, he's a very charismatic and a very persuasive guy. And so, he kept at us and we're like, okay, well, let's talk about this. We're working on this weather station anyway. And so we got involved with those guys and really let the goals of their organization steer some of the early development and some of the design goals for the instrument. So what TOMO wants to do is basically revolutionize weather monitoring in Africa, which there is extremely spotty, very little surface observation in sub-Saharan Africa. In fact, at this point, the TOMO network, which I believe is running 600 stations or something like that in a bunch of countries, is by far the largest operational weather network in Africa at this point. And so there's a dearth of information, and they wanted to fill in all those gaps, both from a, forecasting point of view, but really one of their overriding goals was to try and help the African farmer. So insurance companies will not extend crop insurance to farmers if they don't have a way to actually verify that some catastrophic weather event has happened to destroy the crops. And so this really puts the African farmer in a bind. They can't get any crop insurance, which is, I mean, that's an integral part of the farming systems in the developed world. So if they have a failed crop, they're out of luck, and people are starving. So there's no way to balance out those cycles without good weather observations. And so that was one of the main reasons that Tomo wanted to develop this large network.
There's quite a few all-in-one stations kind of on the market already. Do you think that the sort of unique approach of involving this organization really yielded a more unique or robust design? What were some of the things that they had as a goal that we might have not included otherwise?
Yeah, great questions. I mean, the realities of running field sites, continuous field sites, and trying to maximize uptime on weather observations in many countries in Africa is a bit different from what many of us are used to here. It's difficult to make field trips. That sometimes there's civil unrest and things are quite dangerous. In many countries, it's difficult to find really skilled field crews to go out and maintain the instrumentation. And so the number one goal is low maintenance. And so that's what they brought to the table. They said, look, guys, we can't have any moving parts on this. We can't have any stuck tipping spoons. We can't have any frozen bearings on our anemometers. And we've got to make this thing as robust and maintenance free as we possibly can. We also have to have seamless remote data transmission that doesn't take any human intervention to get data from point A to point B. And so that's why we came with the design with the drop counter, which is a bit of a unique feature that has no moving parts on the rain gauge, and the sonic anemometer instead of a propeller or a cup anemometer. And so those were the things early on that we put as design goals. But I will tell you that well, let me run off into storyland here. So at Meter, when we want to change an instrument and improve it, we run what's called an ECO, an engineering change order. And ECOs, they take a bit of overhead to get all these changes that we want to make and these improvements done, worked through our production team. You have to change all the work instructions. You have to get everything in order, all the new parts. But we have probably run 40 ECOs on the ATMOS 41, and many of these are in response to various things that we've seen from Tomo. Okay, so our process is generally, hey, we see something fail or we see a problem. You see it once, it might be an anomaly. You see it twice, okay, well, there's something there. That's kind of yellow alert time, and so it's time to think about responding to that and making a design change or mitigating that. And so as we see these things crop up in Tomo, so some of the interesting examples might be, hey guys, the whole rain funnel and the drip counters are full of termites and termite eggs. Okay. And they send these pictures through of just these horrendous, colonies of ants and termites inside the instrument itself, which really doesn't help instrument function. Okay. It might surprise you that having a whole termite nest in your instrument doesn't help. So, you see that once, you're like, okay, whatever. And then you see it a couple times, you're like, okay, well, it's time to fill in some holes and add some screens and some different bits to keep the bugs out. And so it's just been a whole series of things like that have come back. And I think at the end of the day, it's made the instrument way, way, way more robust. So, I mean, if they've got, 600 of these or so in Africa, and they're running with more than 90% uptime, which is their goal, then that bodes pretty well for the success of the instrument, where you can actually get to it and maintain it. So
the termite situation was not an isolated incident, is what you're saying?
No, it was not an isolated incident. And the flies, you don't expect, fly nests in your instrument. Yeah, just all kinds of crazy stuff. I should put together a PowerPoint with a collage of all the pictures that they've sent us of like creepy crawlies that are attacking our stuff. And Chod, I'm sure you can probably relate to this. You guys, I'm sure, have, a whole album full of pictures of bugs and logger enclosures and things like that, right?
Oh, man, ants, fire ants, just crazy creatures that can just get in to any kind of crevice or a little small space, and they get in there and they just wreak havoc. They will eat anything. It's impressive.
Yeah, it's amazing. They love cable jackets. Like, what is it about plastic that they want to eat?
They eat it for dinner. It's just it is nuts. Like that cannot be good for you, and they're just chewing on it like rodents. Oh, so crazy.
So how do you keep termites out or bugs out or flies out or fire ants out of a weather station?
Well, you got to plug every hole with either some mesh or just, make the opening small enough that they can't get in. And so, the main culprit with the ATMOS 41 was where the rainwater would come through the funnel and pass the electrodes that count the drops and measure the rainfall, and then a little trough, and then that just pours out an exit, and they were getting in that exit hole. So we had to put a screen over that, which is just another step in the production process. And we also had to change the screen for the rainwater intake right at the top of the funnel. So that wasn't tight enough, and they were getting in through there as well. So those were just a couple of pretty small iterations that we had to do.
And I know that bugs are a huge issue, but also birds in terms of wanting to nest in the top of the rain funnel. Is that kind of a different battle?
I know it's a podcast, so you can't see the really grumpy look on my face. But yeah, birds are the bane of the existence of any rain gauge. I mean, Chod, back me up here, please, that it is very difficult to keep them from perching on a rain gauge.
Oh, rain gauges are really, I think, the one of the biggest problems that we have with birds. They eat anything. We've had them eat wind sensors. We've had them eat, just pecking and just destroying all sorts of things. But you're right. That rain bucket, that opening, it just says, "Hey, I am an outhouse that you want to use."
Yeah, and they're very persistent. So, we did come with a crown, a bird spike ring that sits over the top of the ATMOS 41 or the ClimaVUE, and it's got pretty light gauge wire on it. And the reason for that is we don't want to block any more solar radiation than we have to, because of course we have a pyranometer sitting up there, and you're going to shade that if you have big old thick spikes. But that works super well from my experience and from the experience of some of the folks like Kevin Hyde at Montana Mesonet. We've had really good success with small birds with that, but you really have to beef up those wires if you want to keep the large raptors off. Chod, do you guys have any better methods for keeping birds off? Than just spikes?
Doug, really, the spikes is probably the best method. The big, large birds, it's always been a problem. So I think in a lot of these applications, they would put something else there for them to stand, to sit on. Those will maybe a little bit higher, something that was a little bit easier to stand on, and they'd prefer that. And that's usually all you can do.
Some of those bird spike apparatus, it's not just, vertical spikes, but they've got, all over, kind of randomly distributed. Was wondering if those work any better.
Well, I think they probably work better. The problem is, and you did mention this with the pyranometer, you have to be really careful when you're talking about instrumentation that you don't want to put something there that is going to alter the measurement and the precision of that instrument. Putting something with lots of spikes is probably going to not only hurt the pyranometer on the ATMOS and the ClimaVUE, but it's also going to probably affect the precipitation measurement. It's going to create errors that way. So I think there's always just that trade-off. What are you going to do to keep, at minimum, the birds, and other problems like that at bay, and still keep the measurement as pristine and as high quality as we possibly can? And it's that trade-off, and it's going to just depend on the location, what kind of bird species you have around the area, and what precision and what kind of accuracy are you expecting out of the instrumentation.
Mm-hmm. So that strategy of giving them something else to perch on is kind of similar to a lightning rod that's up above the level of your weather station, so that you get your strike and you get it grounded there instead of basically a sacrificial spot to get fried. So you could do the same with the birds, I guess. Just a sacrificial spot.
Creating and designing a piece of scientific instrumentation is a different type of experiment than what many of us as researchers are used to. So usually you're using a tool to collect your data to reach your objective, but how does the process differ when you're actually designing that tool?
It's definitely a different peer review process. I mean, we were talking earlier, and when you're writing a paper, well, you do your research, you write it up, and you submit it, and you get probably 3 or 4 anonymous reviewers. And depends on the journal. Maybe they're not anonymous, and they critique your work and give you feedback, and you respond to it, right? Well, our job is a little bit different. We have to come with our best effort, right? We do the development, you test as thoroughly as you possibly can, right, with your in-house testing. And then we also send it out to beta customers in different climates and research partners that help us. And that's kind of like an internal peer review. But then when you release it and you start selling it to all the researchers out there, well, then that's your real peer review, right? And trust me, if you have problems with your instrumentation, or if there are things that are issues or things that need to be optimized, those peer reviewers, our clients and our customers, will be very happy to tell you that you need to update your manuscript and make it a little better. So we get continuous peer review from our researcher friends and colleagues for the type of research that we do.
Doug, I love that answer. It also would just state that one of the other differences, I've been involved with a lot of development projects, and in the ClimaVUE, in the ATMOS, I think are some of the ones that stood out to me as really being regimental on making sure, hey, we know what this accuracy specification is because we have a reference. We have things that we can go back to. That's what I think. That's what kind of changes a little bit with doing research and actually developing a sensor instead of just maybe a process to use the sensor in. Is that you do have references, you have standards that what the real answer needs to be, but when you're developing it and you're testing it, you have to make sure, there's ISO standards out there that say this is how you need to do this. And you just need to follow that. It's almost like a cookbook, but at the same time, there's so much physics involved with it and how to make sure that you've eliminated all other sources of error so that you can say, this is my uncertainty with this measurement, and this is how we're going to describe it. It's actually really quite complex, and it's a whole field of metrology. And how to take measurements and how to make good quality measurements out of it. And the meter team, when we took that sensor, one of the very first prototypes, and we started going through, and we started seeing sometimes like, okay, the measurement was great here. Sometimes it was off a little bit, and making sure that how we were testing it and meter, and that we were seeing similar things, and we could, the design and change happened. We could change some of the designs of the sensor if it was something wrong with the sensor. Also, sometimes we found that the sensor was actually right and our testing was wrong, and we got to go back and we could really nail down our testing and how we were testing and making sure that it was right, so that it aligned with where the sensor was already measuring wonderfully. I think the temperature sensor was one of them. It's just the temperature sensor is a really good sensor, but it's actually it's actually really good compared to some of our reference sensors that maybe were put into a shield, and in low wind situations they would heat up, whereas the ATMOS and ClimaVUE, it would stay really where the air temperature really was, and so we'd have to get like aspirated shields. We couldn't rely on the old passive shields to be able to get that measurement.
So that brings up an interesting point. When you're designing a piece of equipment, you're not only designing it, but you're designing a standardized method to test it and make sure it's working. Can you talk about that? Because I know, Doug, you mentioned that at one point someone was driving down the highway with an ATMOS 41 on the back of their truck.
Yeah, well,
just a little bit unconventional maybe when people think about the professional process of designing equipment.
I don't think that's what Chod was talking about when he was talking about ISO certified test methods, like driving down the highway with an ATMOS 41, latched to the top of the truck. Yeah, so a lot of that was, we do some preliminary testing with the anemometer, the sonic anemometer on there, before taking it over to the wind tunnel. So we have access to a nice wind tunnel that'll go to 60 meters per second over at University of Idaho. But, you have to schedule that and get in there. And so sometimes for the early preliminary tests, we do have, generally this is Gale and Campbell. Many of you who might listen to this probably know Galen, but he'll be out there with one of his grandkids, cruising down the highway a little bit too fast. They go drive one way first to make sure there's no sheriffs, and then they come flying back the other way and make sure that they don't get any anomalies, at the high wind speeds. So yeah, that's a real thing, Holly. So one thing that Chod was mentioning earlier was the regimented testing process and, comparing against known standards. And that is spot on that we do have standards for these weather parameters. But one of the big challenges with an all-in-one weather station is that we've got like a dozen sensors in there, right, that all have to be compared to the standard sensors. And so if we were just talking about, an air temperature sensor, well, that's a pretty easy comparison, right? But then keeping track of, the solar radiation, and you've got your vapor pressure, and you've got your barometric pressure, and you got your wind speed, you got your wind direction, you got your gust, all of these different measurements that you have to try and compare against those reference standards. And so that was, a big part of the early work, and actually a big part of the later work. So one of the things that was interesting when we partnered up with Campbell Scientific to, continue the development of ATMOS 41 and turn it into the ClimaVUE was that my main contact there was Alan Hinckley, who was a very experienced meteorologist, late career guy. He's since retired, but I didn't know it at the time. But Alan has the reputation of being extremely exacting. So when he was putting this through its paces, he was really putting it through its paces. And so he came back with some really great input that helped us, improve the instrument, and always did it with a very pleasant manner. So I doubt that Alan will probably listen to this podcast, but just wanted to give him a shout out that really appreciated his involvement with all that.
It was kind of the continued development of the ATMOS and creating the ClimaVUE. We did see a lot of, early on, some issues that I know that the meter was working on. Some of them that they knew about as well. Any development, you're going to have issues. You're going to have things that come up. But that was what I love about meter, and I think that it just aligns really well with what Campbell Scientific believes in as well, is just continual improvement, continually developing it and making it better. You see a problem when it's reported. You investigate it really quickly, and you just drop everything else almost and start looking at how are we going to fix this. We're not trying to sweep it under. We're not trying to just say, well, we're going to just going to have to live with it. We're going to actually try to fix it, and that's something that I really appreciate. Meter, it's just part of who they are, and it's part of in Campbell Scientific. Like I said, that I think those values really align well.
Yeah, thanks, Chod. We appreciate that.
I know Campbell Scientific and Meter Group have some of their origin stories that align, which has kind of facilitated a lot of the early collaboration. But I think it's kind of unique that collaboration has continued, because I think it would be really easy for the two companies to kind of become rivals in this space. So can you talk about how it's really easy for our scientist teams to come together, like you said, to kind of solve a common goal when it comes to just improving science and improving the way that we collect data?
Yeah, I can take a stab at that because I've been immersed in it for many, many years. So, even in grad school back, 20 years ago, I used instrumentation from both companies. And, I was actually pretty good Campbell Scientific junkie, loved programming in Edlog back in those days. But then, joined Meter and found that in many times it was an interesting relationship where there was almost a sense of competition there. But recently, I think we've gotten past that and realized that the research community needs the breadth of offering that we have, right? So Campbell Scientific has these wonderful configurable loggers that you can measure anything in the entire world with, right? But you have to have a learning curve. You have to learn how to program them. And we fit into a different space where we offer a turnkey system that's going to help a whole different set of researchers. And so there's really not as much competition as you might think at face value. And, at the end of the day, both organizations are here to help the research community do their job and try and advance the science. And so we, like Chod just said, we have really similar values, right? And so from that standpoint, it's made it really, really easy to collaborate. And so, I got to give some credit to Kyle Campbell and Joshua Campbell and Chod and Dirk Baker and some of these guys that, have come to the table and we've, formed a really great partnership that I think is still blossoming. So I've been really pleased and really happy to be part of that.
Doug, I appreciate that. I would agree that at times we've been competitors, competing on some of the same projects, some of the same, trying to present solutions for the same things. And absolutely, we're still competitors sometimes. And I think that's healthy. I think it's healthy to a lot of degree, be able to say, hey, we both want to present a solution, sometimes even the same customers, but the customer can decide, what solution fits their needs better, because it's all about making sure that the customer gets what they need. And I think that the meter solution has so many benefits. And then the open platform from Campbell Scientific, if they've got a weird sensor that they have to measure, well, the Campbell Scientific solution can help them with that as well. And I think that's kind of where our strength is and your strength lies as well, of a turnkey solution. And both of those solutions, they're different. You can't have really great configurability and keep it as easy. Those things, they do kind of, they counteract each other. And in recognizing that some customers and some applications, they need one solution, one needs the other. And, as long as we're trying to move toward making sure that customers get the best solution that they need, then we all win at the end. I think that's what we need is always to help the customers.
Right. So when we think about the trade-offs that researchers have to make in terms of how they want to collect their data, what are maybe some of the pros and cons of an all-in-one station compared to maybe a more customizable or piecemeal setup?
Well,
that's a great question. Yeah, Chad, go ahead.
No, this is a great question, and I'm going to just kind of back up just a little bit, maybe to answer this, to just say Campbell Scientific historically has always used individual component sensors. Mm-hmm. That's almost every station that you see that's a Campbell station has the individual sensors and sensing elements, and we haven't done a lot of all-in-ones. We haven't sold a lot of them in the past. And primarily it's because when you're dealing with standards such as like EPA, weather, or the Weather Service, or these other meteorological like WMO, they have standards, and WMO is a big one, and they have standards that say, hey, this sensor or this, like wind needs to be measured at these heights. Temperature needs to be measured at this height, 2 meters, 1 meter. You get these kinds of specifications, and you can't do that and can't measure those heights when you have a sensor that measures them all at one height. That's really one of the biggest issues. The other issue is that sometimes you have certain requirements to say we need really tight accuracy on maybe this measurement, really, really tight on a temperature, or that they demand, say, we need like a PRT in an aspirated shield. Well, you can't do that really easily on an all-in-one either. And so those kinds of applications, you do need sometimes some individual components. But for the majority of researchers and the majority of applications where we're trying to do gap filling in between maybe these reference stations, or what we call these synoptic stations, where they have to meet these standards, it makes a lot of sense to be able to put them all in one. Just install one sensor, one height, make it the best height you can. Precipitation in the UK, they want precipitation at ground level. Well, you can't measure wind at ground level, guys. You just can't. It doesn't work. So, we haven't tried, but I'm just kind of working this through in your mind. And in between spots, in between stations, filling those gaps and trying to make sure that we have a better spatial coverage. The all-in-one stations just make a lot of sense, and it's just I think that's just such a great achievement. Being able to put all of those measurements, precipitation, solar, that's huge. Being able to put all of those measurements in one sensor.
Yeah, and there are definite applications where it's plenty good, and actually the really the right solution. So reference evapotranspiration, where that all those measurements are at 2 meters for FAO. So that makes a whole lot of sense for an ATMOS 41. And you're right, the gap filling in those more widely spaced synoptic stations is just a huge thing right now. So, AgWeatherNet just came out with, this is Washington State University's AgWeatherNet that runs a whole bunch of synoptic stations and also a whole bunch of ATMOS 41s and other all-in-one stations. And they did an analysis of the microclimate effects and showed that, okay, so you can interpolate between really high quality stations that, maybe have 0.2 degree temperature accuracy. And by the time you're a kilometer away, you're off by 2 degrees C just because of microclimate effects. So you're going to be way better off in many cases characterizing your microclimate at your field station or at your experiment or at your growing operation with a localized, a hyper-local measurement of weather. And the all-in-ones are really well suited for that.
Yeah, I think to just back up, Doug, just to let everybody who's listening know what synoptic stations mean. Those are really, we have certain levels of stations, of weather stations globally. And a lot of times they'll have what they call climate reference stations. There's not a lot of them out there. There's actually very few, but they have redundant measurements. They have the top of the line sensors that you can buy, that are available anywhere. In fact, sometimes they make their own sensors just to make sure that they hit the specifications that they're asking for. There's not a lot of those. But right below that are these synoptic stations that we're talking about. Those are the ones that end up like at airports or in these large high-end networks that are measuring weather, that the Weather Service pulls in that data from and is using for a lot of its records, a lot of its other that data. After that, there's a lot of this openness of a lot of different types of stations that are out there, and the ClimaVUE, like Doug said, has really good measurements. For an all-in-one sensor, it has really high-end measurements. And those measurements are perfect, like you said, where you have these microclimate changes. Researchers, or in areas where you're trying to measure what it is in this, this location that's not being served by those synoptic stations. That's a huge win.
So what advice do you both have for researchers who might be considering whether or not to really start investing in this hyper-localized weather data? Maybe if they're just using local weather data at the moment, and they're kind of not sure whether or not they want to take that leap into getting their own equipment set up.
Do it. Get your own, but measure your own. Really trusting a local station that you don't control and just pulling in that data. It can be kind of dicey. Sometimes the data that you pull is coming off of a low-end station and you don't know it. The ClimaVUE would give you a lot better measurements in your location, and your data you're not going to have a lot of those errors that you're going to have to try to work through later as you're doing your analysis, because you'll have had that local data to begin with.
So not only is there the risk that that local station is not really local to you and it's not capturing those microclimate effects, but you're saying actually the measurements themselves might not be as quality as you think, just assuming that you're getting that data, that it's going to be coming from a quality setup.
Yes, absolutely. I know from experience where I live here in Utah that there is a station that's just up from me, not too far up the hill. And the station has a wind sensor that the bearings have gone out.
Oh my
The measurement is really poor. And I know because I drive past it and I can see it. But let me just tell you, it's pulling in one of the really common weather reporting services that you get online.
They need a little sticker on that, like the "How's my driving" sticker on the back of the fleet trucks. Like, "How's my observation?" Call the hotline. if not spinning while windy, then call in and report.
If you see a bird on top, please inform us.
Shoo it off at least. So can I tell a little random story here?
Yes, please do.
This must have been about 8 years ago. Galen and one of our other engineers were banging through schematics and circuit design, like, oh, are we going to use a UART? And, all these goofy technical terms that the engineers like to use to try and, nail down some of the nuts and bolts of the internals of what would become the ATMOS 41. And so I was asking Galen about that, and he's like, oh, well, but the origins of this are way earlier. I'm like, okay, do tell. He's like, yeah, back when I was on sabbatical in England back in 1978, developed this 1D sonic anemometer. And then the next summer after that, summer of 79, did a sabbatical at Campbell Scientific and was working with the 1D sonic and the Lyman alpha hygrometer. And then my brother Wayne, had this idea that if you bounce that sound signal off a reflector, you could actually get horizontal wind speed from that sonic anemometer. And that was kind of the earliest genesis of wanting to do an inexpensive yet robust 2D sonic anemometer, which is really the special sauce of the ATMOS 41. So we've been working on this since 1978, guys. Okay. Continuously refining full time since 1978.
And it's not done yet.
It's still not done. It will never be done. I mean, Chod will tell you, no instrument is ever done, I don't think. And if it is, then, well, either you've achieved perfection, which I haven't seen it yet, or else you're not doing your job right if you're just letting it sit out there.
Well, you're either continually improving it, or you've retired it and you shipped it off. You no longer sell it.
Exactly.
It's done. We're done with that. We've moved on.
What are some of the research trends that you're seeing right now in the field of environmental data collection? Is there anything that you have in the works that you're really excited about, or trends that you're seeing that get you really excited about the future of environmental data collection?
So the research trends that we're seeing, and one of the things that we're most excited about at Meter, is kind of a shift from measuring water content in soil to measuring water potential. So water content in the soil tells you how much water's there, but I would say the vast majority of research, water potential is more important. It tells you, more about water flow. It is integral to plant availability. And so I think we're seeing a trend in that direction, and we're trying to respond to that with some new water potential sensors that are field ready and robust and maintenance free. And that those are some of the things that I'm most excited about. And especially in terms of irrigated agriculture, I think that entire industry, which you can't really lump it into one industry, that's a huge industry with, multiple sub industries. But I think many of those could benefit from water potential measurement. And that's the way that we're kind of moving at Meter, is to try and help the water scarcity problems and help feed the world. I think that's what our next couple of decades are going to be.
I would agree that water potential, I'm not going to use the word potential, but water potential has the ability to give our environmental users, and really not just researchers, but everybody who needs to know about water in the soil, give them a lot better idea of the state of that water, where it's going. You can't tell where water's going, whether it's available for plants or whether it's moving in the soil, without knowing the water potential. And ultimately, the reason we've always done water content is because it was easier to make.
Easy. Yep.
Water potential's hard.
Mm-hmm.
And because of that, water content sensors have just flourished. And water potential sensors have kind of stayed stagnant because it's hard to make them. And it's hard to take the measurement. And it would really be, I think, beneficial, and I think we're seeing that kind of slowly, but I think it's going to be something that we'd love to see change as well, where we start talking more about water potential in the soil, and really how it translates into plants as well. Whether ecologically or agriculturally or whatever, in any realm, those are some of the most important topics to finally come to a fundamental understanding of, is what's happening to the water, where it is, and how are we going to optimize the scarce resource that we have.
That's right. That's exactly right. So you were asking about other things that we've got going that we're excited about. We are working on packaging our telemetry, our wireless technology, into the ATMOS 41. So it would be, these exist. They're on our roof right now, but a fully wireless weather station that you just bolt down on top of a post and walk away, and your data, flow directly to Zentra Cloud with no more installation than that.
I love that. The Atmos really does. I just to say this because I think it's true, but I really believe it. The Atmos really, I think it's set up to be very successful in these IoT kind of situations with the low power, every single measurement integrated into the one sensor. Mm-hmm. It's it's just makes a lot more sense than some of the other all-in-one solutions that really do have a lot higher power. There's just no way to really have that plus the telemetry and keep it on a power budget.
Yeah, right. Yep.
Well, our time's up for today, so thank you so much to both of you for taking the time today to talk to us about the ATMOS 41 research trends, birds, termites, and we wish you the best of luck in your future research and future collaboration.
Thanks, Holly.
If you have any questions about this topic or want to hear more, feel free to contact us at metergroup.com or reach out to us on Twitter at meter_ENV. As always, I'd love to hear your thoughts. My handle is at HLPlants. You can view the full transcript from today in the podcast description. That's all for now. Stay safe, and we'll catch you next time on We Measure the World.